So with this in mind, let's look at questions from homework 1.8. So remember that a transformation is linear if it respects linear combinations. If the image of the combinations is the combination of the images. So let's look at some of these problems. One of the problems that we want to look at is 12. So A is the matrix in exercise 10, and we want to determine if B is in the range of the linear transformation X to AX. So let's take a look at this matrix. And let's think about all the equivalent questions that we have for this problem. So A is this matrix, 3, 1, 0, 1, 2, 0, 1, 4. This is by columns, 2, 0, 1, 4, 10, 2, 2, 10, and then -6, -4, 3, 8. And B is the vector -1, 3, -1, 4. And so the question is B in the range of the transformation? So the question says, is B in the range of the transformation X to AX? So there's a linear transformation that goes from looks like R4 to R4 in this case. And we want to know if B is in the range of this transformation. This is equivalent to saying, is B a linear combination of the columns of A? So alternate formulations of this question. Is B a linear combination of the columns of A? Is B a linear combination of the columns of A? We could be asking a question in terms of equations. Is AX equal B consistent? We could say, similar to linear combinations, we could say, is B in the span of the columns of A? Is B in, I spelled in wrong. Is B in the span of the columns of A? All different ways of asking, is B in the range of the transformation X to AX? So the one that we want to focus on is that equation one, because this equation one will lead us to an augmented matrix. So we're going to key on this equation one, and we're going to say, since we want a consistent equation, so does the augmented matrix A, B have a pivot in its rightmost column? So that's the matrix question that we want to look at here. We need an augmented matrix to determine if AX equals B is consistent. So what we need to do is find the reduced row echelon form of A, B. And look at that last column. Any questions? If there is a pivot in the rightmost column, then AX equals B is inconsistent. Then B is not a linear combination of the columns of A. Then B is not in the range of the transformation. If there is not a pivot in the rightmost column, we would say that AX equals B is consistent, and that B is a linear combination of the columns of A, and that B is in the range of the transformation. All things that we would get by looking at that rightmost column of the augmented matrix. Any questions? Cool. So put all that stuff into an augmented matrix and find the reduced echelon form. I recommend using a machine to do it. In problems 24 and 25. So in 24, we want to show that this transformation is not a linear transformation when b is not 0. So the most efficient thing to do for 24 is show that the image of 0 is not equal to 0. If t is a linear transformation, then t of 0 is equal to 0. So for 24, oops, I should label this. This is 1.8, 1.812. In 1.824, we want to, we can use the fact that linear transformation respects linear combinations. So since a linear transformation respects linear combinations, if t is linear, if t is a linear transformation, then t of 0 is equal to 0. We can turn this around by saying if t of 0 is not 0, then t is not a linear transformation. If t of 0 is not 0, then t is not a linear transformation. That's called the contrapositive. We always get the contrapositive. If A, then B means that if not B, then not A. This does not mean that if t of 0 is equal to 0, we can conclude that t is a linear transformation. But if t of 0 is not equal to 0, then t is not a linear transformation. We don't get the converse or the inverse, whichever that one is, but we do get the contrapositive. So if b is not 0, then t of 0 is equal to just b, which is not 0, and so therefore t is not a linear transformation. So pertinent to this problem, if b is not 0, then t of 0 will equal b, which is not 0. Therefore, t is not a linear transformation. No, a linear function is different than a linear transformation. F of x equals mx plus b, where b is not 0, is still a linear function, but it is not a linear transformation. Not a dumb question at all. We mean different things when we talk about linear transformations versus linear functions, even though transformations are just functions. So that is 100% not a dumb question, and it's a perfect question, because we're using linear in a very different way here, aren't we? Because here a linear transformation means some very specific things. It has to go through the origin. But what we call a linear function is not necessarily a linear transformation. So, perfect question. That's exactly what you're supposed to notice as well. Whoever wrote problem 24 is like, oh, dude, this is going to be perfect. Someone's going to be saying, oh, but what about these other linear functions? I'm like, oh, we're talking about something kind of different here, aren't we? In 25, we're given that v is not 0 and p is an Rn. The line through p in the direction of v has this parametric equation. Show that the transformation maps this to a line or to another line. So in 25, we're just going to use the fact that a linear transformation respects linear combinations. So v is not 0, and p is some other vector in Rn. So if I want to do t of, what is it, p plus, see, this is just kind of jerk move on, they use t for the parameter. kind of a jerk move, but all right. We're just going to use the fact that t is a linear transformation. So we want to say this is either a line or a point. And they refer to the point as a degenerate line. I love the fact that we use such disparaging terminology for degenerate lines. So if b is not 0, so the question is, how does b not equal 0 not respect the linear transformation rules? If b is not 0, then the image of 0 under the transformation, so the image of 0 under the transformation, I left out that detail, t of 0, t of x in this transformation. So in 24, the transformation t of x was ax plus b, was equal to ax plus b. So that means if we do t of 0, we get a times 0 plus b. A times 0 is 0, but b was given as not 0. So the image of 0 under this transformation, ax plus b, is not 0 because it ends up being, because we're left with the b. So in 25, we want to show that p plus tv, which is a line through p in the direction of v, is either a line or a point. If t of 0 is not 0, then the transformation is not linear. There's nothing wrong with it, but that means the transformation could not be a linear transformation. Because to be a linear transformation, the image of 0 has to equal 0. That's not a random rule at all. So a linear transformation is a linear transformation if the image of a combination is that same combination of the images. What that means is that I have to be able to take any vector x, if it multiplied by 0, I get 0. So a transformation is a linear transformation. T of 0, which is just 0 times any vector, has to be 0 times the image of that vector. So in particular, t of 0 times x has to equal 0 times t of x, which is definitely 0. This is for any vector in x in Rn. So t of the 0 vector has to equal 0. If t of 0 is not the 0 vector, then the transformation is not linear. If t of 0 is not 0, then t is not linear. So that's the rule that we used in 24. That was the convenient thing. We could just go take it and go right to the first principles and show that it doesn't, the image of a scalar multiple is not the scalar multiple of the image. All right, so we're going to use a similar thing. 25 asks a similar question. So the image of a line is either a line or a point. The image of a line is either a line or a point. That's what 25 is asking. So we're going to use the fact that since t is linear, the image of p plus t times v is the image of p plus t times the image of v. Because t is linear, t will have to respect the combination. T of p is still a point, and t of v is either a one vector, so that makes this a line, or t of v is 0, in which case this is just a point. So now we have cases. If t of v is 0, then the image is a point. If t of v equals 0, then we get a point, specifically t of p. If t of v is not 0, then we've got a line. A line through t of p in the direction of t of v. So that's how our thinking goes with 25. So in 24 and 25, we use the same thinking. A linear transformation respects linear combinations. That's what we needed for 24 and 25. Any questions on these or any other problems from 1.8? How's everybody, okay? Cool. Let's pause the video and switch over to 1.9.